Hello everyone, welcome to this tutorial. My name is Sentinel-2. I'm a Google Earth Engine developer. In this tutorial, I'm gonna show you how to calculate the water turbidity using Sentinel-2 imagery in the Earth Engine platform using Python API programming. At the end of this tutorial, you will be able to calculate the water turbidity in the river mouth. River mouth is a place that the river flows to the lake. So as you can see, at the end, you can interpret the turbidity dynamics through the time, and also you can plot multidimensional variation. So now I'm gonna show you how to do this procedure from scratch in the Earth Engine platform. Just make a new notebook in the Colab environment and start scripting as follows. This is my YouTube channel. There you can find several Google Earth Engine tutorials applicable for the earth science and climatological studies. So let's subscribe and also follow the tutorials to increase your knowledge about the remote sensing application in the earth science. So let's get started. In the first step, I need to call essential libraries we need to make a connection between Colab and Google Earth Engine platform. So start with import EE and GEE map. These libraries are essential to deal with the Google Earth Engine in the Python environment. And also we need the Xarray as XR, and also we need XEE library, but the XEE is not built-in available here. We need to install by pip install XEE library. Let's run the cell. If you search about the XEE library, you will find a GitHub page, github.com, a XEE page actually including a detailed instruction about how to use the XEE and how to combine the Xarray and Google Earth Engine. The XEE is one of the newest libraries developed by the Google community that you can see here, allowing us to combine Google Earth Engine data and Xarray format. It's really interesting things because allowing us to apply Python algorithm on Google Earth Engine datasets. Okay, let's clear the output and go to the next step. Now we need to install, or we need to establish a connection between Earth Engine and Colab. Start with authentication from EE library and then initialize your own Earth Engine account. The first argument is the project ID. So go to the code editor environment and upper right, there is a panel here. Go to the project info. There you can find your own cloud project ID. Just copy and paste into your code, just like that. The next one is OPT URL. So the OPT URL already mentioned in the XEE page in the GitHub. There is a detailed instruction about the XEE, and there you can find the OPT URL address, just like this. Let's run the cell, and after a few moments, a message pops up and asking you permission to access to the Earth Engine account. Select your account and then click on continue and continue. Now permission granted by the user to access to the Earth Engine account through the Colab environment. From now on, we can have access to the Earth Engine data catalog functions and capabilities under Python scripts. So, before I start programming, we need to set the region of interest. So, we need a map for the region of interest. Create a map like this. From GEE map, call the map function with the base map satellite with a satellite background. Let's run. There you go. Now we have a user interface, or we have a graphical map allowing us to select the region of interest using drawing tools available here. For example, in this tutorial, we want to calculate the water turbidity for the lake. So it is important to select a water body for your study area. So you can choose any water body in all around the world. But I prefer to choose a water body in my own country, Iran. Originally, I'm Iranian, and now I can show you one of the lakes here. For example, in the south of the Iran, we have a lake here. I don't know if it is a reservoir or a lake, or anyway, we have a surface water body, and here I'm gonna select the river mouth in this location. What is the river mouth? River mouth is a location that rivers flows to the lake, and I want to select this area and monitor the water turbidity dynamic using Sentinel-2 imageries. So it's very easy to do. Just select a rectangle and draw something like that. So the study area selected, it's really easy to do, and also it's not a big deal. And then go to the next code. Now we need to have the rectangle as a variable in the code. So to do this, make a new variable like the ROI. From the map, select the last feature, draw last feature, just like this. Convert it into a geometry and let's run. As you can see, the rectangle now is available as a polygon with 5 vertices. So you can see the coordinate of the region of interest. Go to the next step. Now we need to call Sentinel-2 imagery in the Colab environment. Okay, make a new variable Sentinel-2 and make a tuple, and inside the tuple, as AI actually suggested, we need to add Sentinel-2 image collection. I prefer to write the code actually myself instead of using the AI assistant. Actually, the AI assistant is really helpful and very useful, but try to write your own code because in this case you can learn how to do programming. An AI assistant could be very useful when you face with a challenge in the programming, then you want to ask some questions. The AI can help you to find the problem and help you to learn how to solve that problem. So, but here I prefer to write the code as much as I can. If I face with any challenge, then AI assistant can help me. So, sir, if you search about the Google Earth engine and Sentinel-2 imagery, you can find the harmonized MSI product, multiple actually Sentinel-2 imageries available, harmonized version level 2A. There are two versions, level 2A and level 1C. Level 2A is atmospherically corrected, level 1C it's not atmospherically corrected. But we prefer to use the corrected version for spectral indices. It is necessary to choose that product that is fully corrected for your analysis. And also you can see the dataset information here, the collection snippet helping us to call this dataset into the Python environment. Let's copy the snippet, and then we need to actually define some temporal and spatial filters. That filter bound like this bounds our data to the region of interest. That filter date, we can actually call images for 2024 or any other years that you want to study. For example, I'm gonna study the monthly variations of turbidity in this area. So that's why I prefer to choose 2024, 2025. Although it is not monthly, Sentinel-2 is not monthly, it's 5 days temporal frequency, but I can convert it into the monthly frequency in the next step. I will show you how to do this process. But my target year is 2024, and I want to see how turbidity changes in this year with monthly frequency. So now the dataset called, let's print the Sentinel-2 and see what do we have here. As you can see, there are 74 elements available here. Go to the features, drop down the features, and now you can see the all elements. There are 26 bands, but not all of them main spectral bands. Only 13 bands available here as a multi-spectral version, and the rest of them are complementary bands that you can use for the pre-processing and extra analysis. So now let's go to another link here. If you search about the Sentinel-2 and turbidity index, you can find the NDTI for NDTI index. The NDTI is a kind of index, a normalized relationship between the red and green band that helping us to highlight the turbidity in the surface water body in Sentinel-2 imagery. Now I need to actually select the water body first using NDWI and then calculate the turbidity index using NDTI in the code. So to do this procedure, we need to define a function and do a multi-step processing. So to do this, let's make a new function. The function begins with the DEF, and the function name is turbidity because the main target is calculate the turbidity index. The input image, we have 74 image. Each image considered as an IMG in this format. And now we need to start actually coding to calculate the NDTI. Before doing this calculation, we need to consider some pre-processing step. The first pre-processing step is the cloud cover. As you know, cloud cover always actually cause significant impact in the accuracy of our estimation. So it is important to get rid of the cloud cover in the first step. Sentinel-2 cloud probability is a kind of data set allowing us to actually manage the cloud cover really easily, very easy. There is a probability band ranges from 0 to 100 that shows the probability that the pixel is cloudy. So we can actually select a clear pixel by a simple threshold. Its resolution is also 10 meter. So to do this, we need first make a link between current Copernicus data set and also the cloud probability band, because we need to have the cloud probability band in our main data set to exclude the cloud and do the rest of the analysis. So how we can do this? There is a function in the Earth engine, link collection, just like that. And now I can make a link between these two kind of collections. Just import the snippet for the second collection, and then we need to have the collection band name. The band name is the probability. Just copy and paste. So let's remove the function and run the cell again. After a few moments, here you can see again we have 74 elements, but if you drop down the features here, you can see a new band added, that is probability. And we didn't have it before, but now the probability is available. So now let's back to the function, turbidity function. Each input considered as an IMG here now. Okay. And the first is the band, a cloud band sets to from input image, select the probability band. So this is the probability band. So, and then we need to find the cloud free pixels. In the probability, pixels with lower values showing actually clearer situation with actually less affected by the cloud cover. For example, here I have a cloud pixels less than, for example, 20% actually considered as a clear pixel in my case. And then in the next step, okay, now we have a binary image including 0 and 1. 1 correspond to the clear pixel, and 0 show actually highlighted or remove the cloud affected pixels. Okay, this is a mask that I can apply it on the final result. So now we need to go to the next step. Before going through the turbidity, we need to calculate the NDWI, because the NDWI help us to separate the water and non-water pixels. So now Before NDWI calculation, we need to select the surface reflectance bands. Go to the Sentinel-2 datasets here. You can see all the bands or surface reflectance bands starting with B and band number. So that's why I can select them with this format. Dot select all the bands starting with B and the rest of that no matter. So there is a scale factor here and we need to apply the scale factor before further calculation. This is a kind of pre-processing we need to do. So sorry, something's wrong in my keyboard and I need to reset the keyboard, and also it takes a few moments. So if you face with any challenge regarding to this tutorial, you can go to my YouTube channel and there you can find the code example and compare yours with mine. Okay, now the problem is solved and I can continue. Oh, sorry, still I have a problem. For just a moment, I will pause a video and then we will back to the tutorial. Okay, sorry for a small interruption in the tutorial. Now the problem is fixed and I can continue. So, where were we? And multispectral image selected, multiplied to the scale factor. Now the dataset surface reflectance bands are ready for NDWI calculation. So here I have an NDWI called the surface reflectance bands and calculated normalized difference between band green B3 and near infrared band number 8. If you go to the data description here, you can find the wavelengths and also the band name. Band number 3 named as a green, and also band number 8 is a near infrared. So the normalized relationship between these two bands allowing us to highlight the water body with a good accuracy. So the output name is NDWI, just like this. And now I need to select the water and non-water pixels. So water body sets to and get the NDWI pixels greater than 0.1 showing the water body to my experience. And then now we can calculate the turbidity. We have a water mask, we have a cloud mask, and now everything is ready to calculate the turbidity. There are different calculations or different equations for the water turbidity in the Sentinel-2, but one of the most typical version is actually the normalized relationship between the red and green band. So now turbidity NDTI sets to again get the surface reflectance bands. This is a normalized structure, so we can use the normalized difference between red and green. So what is the band red or what is the band green? As you can see here in the band description, band green is band number 3 and red is band number 4. So the equation is red minus green, red plus green. First red band, band number 4. The second is band green or band number 3. And the output is NDTI, so turbidity. So the function finally return the NDTI as a final result, but it should be masked based on the cloud free pixels and another mask based on the water body update mask, because we want to have clear pixels over the water body, so we need to apply the cloud free pixels and water body pixel mask water body. Remember to copy the properties. There are some metadata or some properties in the input that should be still available in the output, specifically the system time start. The system time start or acquisition date allow us to do the time series analysis in the next step, and also it is very important to have all of them. So the function is now ready, but this is a raw function and we need to apply it on Sentinel-2 images. So the map is a loop structure that allowing us to apply the turbidity function on each data available in the Sentinel-2. Let's run the cell, and so there is a problem here. We have no something like select. Yes, it should be select. There is a typo here. Problem is solved. Let's run the cell again. Again, 74 elements return, drop down and go to the feature. But here this time only one band NDTI is available. If you go to the properties, system time start is also available here. Okay, now everything is ready and we have a Sentinel-2 NDTI image with 5 days frequency. But my target is actually the monthly frequency for NDTI. So now in the next step, now we can use the XEE library, XEE and Xarray libraries to actually convert an image collection into the Xarray format. Now I'm gonna actually bring this dataset out of the Earth engine into the Python environment and convert it into the Xarray. Then I can use the Python standard and scripts on this dataset to do more analysis. So now a new variable ds created from Xarray library called the open dataset. So the input for the dataset is the Sentinel-2 image, but we need to define the pixel size, coordinate system, and etc. The first thing is the engine protocol should be EE, CRS or coordinate system should be EPSG 4326, and scale value 0. The scale is the pixel size. The pixel size here is based on degree unit. 1 degree 100 kilometer roughly. So 0.1 10 kilometer, 0.011 1 kilometer, but I prefer to have 30 meter resolution here. So this is a 30 meter resolution based on a degree. We can have 10 meter resolution, but I prefer to 30 meter because 10 meter actually offering too much detail. Maybe it's not necessarily need, but if you want to have the 10 meter, you can add like this. This is now 10 meter. But remember that when you have actually the 10 meter data set, the speed of processing is slower and takes more time to do the analysis. Let's try with 10 meter, and if the process was too low, then we can actually back and turn it to 30 meter. So now geometry should be ROI or the region of interest. Let's run the data set. Okay, the data set is now ready. Let's print the data set and see what's the difference. Here we had an image collection format with a feature, a structure, and all the data listed one by one, and also based on the time order, and we had a band properties or something like that. But now the structure, everything is changed. We no longer have image structure. Here we have only an array of values. Array of values about the time, longitude, latitude. Instead of a band, we have a variable. Its data set available along the 3 dimensions: time, longitude, and latitude. So in the next step, I'm gonna actually here show you how to proceed this data set in the next step. So the data sets, and now first of all, before going further, we need to sort it based on the temporal order. So ds.sort by time dimension. There are multiple dimensions here: time, longitude, and latitude. First of all, we need to sort this data set based on time, because sometimes we have some misorder problem after conversion. So then multiply the out values to the 1. Scientifically, nothing happened after multiplication, but to my experience, when we apply a simple equation after this conversion, Actually, that allow us to create a new dataset separate from the original one and speed up the processing in the next step. That's highly useful. It's a kind of trick. This is not a scientific things. So let's run a dataset. Nothing changed in the dataset, just we ensure that the data sorted based on the time without any challenge. So now we can convert this dataset into the monthly format, for example. Call the dataset and then throw the Python function like resample. We can convert it into the monthly average or monthly median. Monthly median, the median along the time should be calculated. So let's print the DS monthly, and now you can see we have 12 time images. So 12 time NDTI, and now let's plot it. It's very important because we need to see that actually how the output looks like after doing this analysis. So the DS monthly get the NDTI band first, just like this, and make a plot. X axis in the plot should be set to the longitude dimension. So you can see we have a longitude dimension. Y-axis should set to latitude dimension. We have a multi-temporal data set. That's why the call should be actually set to time, and the robust increases the contrast in the output. And then we have a multi-temporal map, so I need to have 6 plots per row. Here called wrap should be 6. Let's run and see how the output looks like. Okay, now as you can see, we have a turbidity map that shows actually how turbidity varies from one location to another location. So, and you can see the changes through the time, and the lighter areas showing the higher turbidity and darker areas showing the lower turbidity. Even we can decrease the spatial resolution and see how the output looks like. But here you can, if you want to change the output color structure, CMap, for example, could be here. Combination of, for example, we can have a cool warm, for example, cool warm. Let's run, and here you can see the reddish area with more actually turbidity and a bluish area with the lower turbidity. And you can see at the entrance the actually the river mouths where a river flowing to the lake, the amount of the turbidity is a bit higher. So, and even we can apply this this algorithm to another region and see how it looks like. So now you can see here in my previous example, you can see actually how the area looks like. And here we got the median. Even you can change the operator and see how different operators works here. For example, I changed to the average, and now you can see the values is a little bit increased when we change to the average. Or we need to have, for example, the maximum of the turbidity for every month. So let's see how it looks like. The maximum is a very high value. The maximum actually goes beyond the positive values 0.4, or even if you want to increase the contrast, you can set the Vmax to, for example, 0.1, for example. So that's highly useful to increase the contrast for the output. Now you can see with the better quality how the output looks like. Or even you can have the sum of the turbidity through the time. It's totally up to you how to proceed. So now we have the sum of the values, but the background is annoying. But anyway, you can change it to another operator, or even you can have the minimum. So let's change it to the maximum because I need to have the maximum turbidity through the time. So, and also as you can see, it's a cloud free and with a good quality. The Vmax sets to zero point 0.2. Now the accuracy, the quality of the visualization is a little bit higher. Even now the code is ready and we can apply this algorithm in different areas. So for example, this location was in Iran, and now I can actually apply it on a part of the Persian Gulf here. For example, here, just I can create a little bit bigger rectangle to actually cover this area, the river mouth flowing to the Persian Gulf. And let's run the new ROI, and just by changing the ROI, I can see how the turbidity looks like in the new area. So as you can see, more images available and the resolution is 10 meter. Now, definitely it takes a bit longer compared to a small location that we had before. This area is a little bit longer, and maybe we need be more patient for the analysis, because when the study area gets bigger, then you need to spend more time because the data set is a little bit heavier, and now the process takes longer because we have more pixels, more values for the analysis. Now you can see the data set is still in the progress. For such kind of the area, when the study area gets bigger, you can actually decreases the pixel size from 10 meter to, for example, 30 meter, because the quality of output is still good in the 30 meter, and the data set is a little bit lighter and you can do analysis easier. For example, if I see the executing process takes too much time, now it's about 1 minute, then I can go back and change the scale value and go to the next step. If you face with any challenge in this tutorial, the code link example is available below this video on my YouTube channel. There you can find my code and compare with your own and see how it works. And please share this tutorial with all remote sensing experts in all around the world, everyone who wants to know more about the Earth engine and remote sensing. These tutorials could be very helpful. For example, here you can see it's taking too much time, and I can actually stop the process here and go back and do some modifications. For example, now I'm going back and reducing the pixel size to 30 meter. Now we have the 30 meter, and here we have a RAM, and also you can see when the data set is very heavy, and in this case the system RAM goes beyond the limitation and the code will be crashed. So we need to consider how much the space do we have for the analysis. That's why I say it is important to manage the scale and also to manage the study area size. If I see the study area size is a very big, then I will prefer to even still reduce the pixel size, for example, to 100 meter, because it is very important to manage the existing RAM and existing resources and getting the good accuracy for our estimation. So the code is still in progress, but the RAM is increasing. That's a problem. So it sounds actually the system actually goes beyond the limitation, and also it's about 1 minute past, and I think it's good to stop, and let's try with 100 meter. Let's run with the 100 meter. and see how it works. Sounds this area, the area I've selected is very big, and that's why if you, for example, for such kind of area, if their location is or study area is very big, it is better to use Sentinel-2 images or Modis images. That's why we prefer to use the Sentinel-2 imagery for the local studies, because it's a spatial resolution. The 10 meter is only useful when your location is very small. So in that case, it is easier to manage the process. So now you can see after in 100 meter resolution, after 35-second process is done. Hopefully we still have storage for the analysis. So let's convert it into the monthly format and let's run it again. Now we can see the maximum value, the monthly maximum value for the river mouse in the Persian Gulf, and now you can see actually how the area looks like in this new figure. And you can see in the entrance in the river mouth, or where the water body is a little bit shallower, you can see the turbidity is higher. That makes sense. So now you see that how we can change the location and get the results. Even here we can actually get the average in a for example CSV file through the time. For example, here you can see the DS monthly dataset is available. Let's run the DS monthly. We want to get average for whole of the time. For example, we want to get average for every time over the location. It's very easy to do. Here we can have, for example, DS min sets to get DS monthly, calculate the average over longitude and latitude dimension, just like this. So convert it into a data frame, just like this, and DS min. As you can see, now we can have the average for this area and make a plot, and now you can see the dynamic of the NDTI through the time. Sometimes the value is lower, sometimes the turbidity is lower, sometimes turbidity is higher, and you can easily get export by to CSV. That's to CSV, just like that. So the turbidity map with CSV formats. That's CSV. CSN is wrong. CSV. Go to the left panel, and here you can see the CSV file is ready, easily downloadable without any challenge. And also you can do a double click and also see the temporal dynamic of the target index. I hope you liked this tutorial as much as I did, and I'm asking you to share this tutorial with all the users in all around the world. And also you can subscribe on my YouTube channel and have access to several Google Earth Engine tutorial about the remote sensing applications in the earth science. Thank you for your attention.